Hello everyone, I'm Dharam Singh and I will be teaching you physics and math. I'm aspiring to become a scientist and or a researcher, you can say, to be very particular. And my field would be theoretical physics. So I have a deep inclination or love towards physics and math, to be really frank. And I'm going to be pursuing a master's from one of the Indian Institutes of Technology, and then I'm going to go for my further studies. Simultaneously, I also like teaching, so I'm going to teach. You can take a look at my achievements and at my ranks because I have secured all India ranks in multiple exams from the section which is given. I have uploaded a file. And now let's start with the lecture. Today I'll be teaching modern physics. Uh, Also, because this is one of the most interesting and most studied branch of physics. This comprises of three branches, to be very rough at this point. The first branch is the first branch is atomic physics, or also known as nuclear physics. The second branch is quantum mechanics, which is one of the most uh, rigorous branch, I can say, and it has things which are very absurd, theories which are very absurd. And quantum physics or quantum mechanics, either else. And the third branch is general relativity or just relativity in that sense. Relativity was postulated by Albert Einstein. Quantum physics was brought up by Max Planck, and the atomic physics was has been um, a field of study which is very prolonged and has big history. It started back when there was plum pudding model, or before that when uh, Permanu or the indivisible uh, particle or indivisible atom was constituted because people started thinking as to what is inside matter and how deep can we go. So quantum physics was is relatively new and relativity is also new. Quantum physics was postulated in 1905 when Max Planck got over the fact that photons or light particles, it was in packets, and it had packets of energy. So from that packet of energy, he constituted the name quanta, and that quanta gave out the name quantum physics. Relativity was postulated also in 1905. Coincidentally, Einstein gave out five papers of his, which were revolutionary for that moment. And one of his papers mentioned electrodynamics having absurd effects. So, electrodynamics having absurd effects. Just a second. Electrodynamics having absurd effects like the Lorentz factor coming into play. And from there, in 1911, he finally gave out that yes, there is something which can lead to us understanding that time is not absolute. For all the theories before this, all the Newtonian theories or all of mechanics, time was absolute, as in time does not change for me and you and for any other observer. But yeah, it does. So in today's lecture, we'll be briefly talking about atomic physics. So atomic physics was very old, or is very old, because people started thinking that what is inside matter. Obviously, if you look at a if you look at a figure made out of Lego, you'll always understand that these are made out of Legos, small Legos. So those are the things which constitute to that structure. So simultaneously, if you look at your table or if you look at a chair, you'll think that what is inside this chair. Okay, there might, if you are looking at wood, you'll tell yourself, yeah, there is cellulose, but what is inside that? What is inside that? And this kept going and going and going and going. The first and foremost theory which was put forth, and which was a bit rigorous, was the plum pudding model. प्लम पुडिंग मॉडल gave out the theory that जैसे प्लम का पुडिंग होता है, that that resonated with the picture of an atom. So suppose this is an atom. So, and suppose these are the plum pieces which are inside the pudding cake. These were electrons, small patches. Okay, and everything else which was there was just proton. So there is a large part, or you can also imagine this with a watermelon. The watermelon is a brief example, by the way, because of seeds. The watermelon seeds are the electrons, and whatever is the red part inside a watermelon is protons. But this wasn't correct. How did they come to know that this wasn't correct? Is by a experiment. Is by an experiment. So the experiment which contributed to a broad expansion in this field was gold foil experiment. Gold foil experiment was actually given the name of Rutherford's gold foil experiment because it was, the idea was constituted by Rutherford, but in reality, there were two of his students, Giger and Marsden, who were doing, or who were conducting the lecture, or who were doing the experiment. The gold foil was kept in this manner, in a curved manner. And there was a box. This box had a source, alpha particle emitter. It can be any radioactive nuclei or a radioactive element which emitted this. And this emitted a beam of several nuclei towards this. There was a gold foil kept here. This was a gold foil. And this gold foil, I'll draw everything in gold. Just give me a second. This gold foil had gold nuclei. So every ray which was passing through here had to go through this foil, and now imagine the cross-sectional area of this gold foil. These are the nuclei or the atoms of the of gold inside this foil, right? Now what? And we'll minimize more. We'll minimize more. So और minimize करेंगे. So what we'll see is this. that there are several atoms. Okay, now we have to understand how these atoms work. They are being bombarded by another nuclei. So I'll tell you how we understood that how these atoms work. So these beams of nuclei, they came, and most of the beams went right through you, right through you. So most of them were undeflected. The first point that they inferred from the experiment was most of the ray were undeflected. Second, some of them deflected by a small angle, a small degree. So some of them got a little deflected. And very minute number of beams or number of rays, not beams, number of rays were perfectly deflected or almost 180-degree deflection. So very minute number of were completely deflected. And the number is like 1 out of 10,000. So it is very minute in scale. Why was this happening? Rutherford gave out this explanation, and which was correct for that time, that almost all of the space in an atom was empty. Just in the center, there was a point which was heavy, dense, and compressed, but it was very small. So what was happening? The nuclei were coming, and they were most of them were going undeflected because of the empty space. Some of them which were close got deflected, but most of them went undeflected because of the empty region. This ray or this ray of nuclei got completely deflected, but this is very small amount or very small cross section. So hence the probability was very minute for it to be completely deflected from its trajectory. Okay, so this led to the general or the most famous picture of an atom, which was that there is something in between, which we call, or which we have coined the name as nucleus. And there are particles, another subatomic particles, which revolve around the nucleus. Now, what does the nucleus comprise? So there were multiple experiments, multiple people came in, multiple things took place, and we slowly understood that there are electrons which are negatively charged particles. Negatively charged. And there are protons which are positively charged. Then, uh, then these both in a neutral atom were equal in magnitude. Like the number of electrons and the number of protons were always equal. Also, the charge carried by an electron and the charge carried by a proton are the same. Just the thing that is different is the sign. And the charge on electron is negative 1.6 into 10 to the power minus 19, coulombs. That is, coulomb is the unit of charge, and charge on a proton is positive 1.6 into 10 to the power minus 19 coulombs. So these both cancel each other. For a neutral atom, the number of electrons and the number of protons are the same. So the charge, the net charge is zero, and so the atom is neutral. But the next thing was that mass did not add up. So mass of an electron and a mass of a proton were not equal to the mass of the atom. So they constituted, or they understood that there was something more, this X factor, which gave out excessive mass to the atom. And this excessive mass, what was it? So they coined this thing as a neutron. What does a neutron have? A neutron only has mass. It does not confine charge, because if it confines charge, then the atom would not be neutral anymore. So this X particle only gives mass. X does not have charge. The X particle was coined as a neutron. And the mass of a neutron is almost equivalent to mass of a proton. Just that it's slightly higher than the mass of neutron. Mass of proton, sorry. Proton. Yeah. So mass of neutron is slightly higher than the mass of proton. Okay. And the mass of electron is almost negligible in comparison to both of these. So most often when we are doing atomic physics, we just ignore the mass of an electron. Thank you. That will be it from me for today's demo lecture. I hope you enjoyed it. Thank you.